Well, welcome to the Structural Modeling video conference for February 2020. Today we're going to talk about the systems integration modeling and application overview. This will be the beginning of a process where we're going to create a specific example. And right now we've got the city of Seattle, which we've talked about in other papers, or if there's a different example that someone else would like to use, we'll be open to working with people to find the structure, an example that we can use to allocate and talk about these different application structural types, what types of context are they used in, and where they're actually, what their purpose, what their function is. So before we've drilled down into a lot of the details of specific techniques, talked about the different techniques, rated, evaluated them. Now we're stepping back up a little bit in the abstraction level. We're going to set a context where we can then carry a specific type of problem all the way through at a little bit higher level using all the different techniques. We'll be doing that in the next papers to come. So in this specific paper, we talk about the difference between the systems mode of discovery and the systems mode of design. We talk about Kepler discovering the solar system, the relationship there, reducing that specific mathematical set of taking the data and creating the laws of planetary motion. And then we talk about Kennedy with the idea of actually putting a man on the moon. We're essentially setting a goal and an objective, which was the mission system or mission objective, which spawned and created a very large number of other detailed and complex industrial systems and social systems to meet that specific mission criteria. And so we map this over the idea of the systems mode. So in design mode, we have the idea that you know the relationship, you know your mission function, you know what you want to have happen. What you have to do is design the objects and the processes and methods to create that relationship. And in the discovery mode, like with Kepler and the planets, he knew the object, he knew the planets, but he had to discover the real mathematical relationships and formulate those to create the laws of planetary motion. So covers a wide range of systems, obviously a theoretical system like the laws of planetary motion, and real social technical systems like whatever it takes to put a man on the moon, which was a lot. So we're just introducing these two types of system modes so we can more clearly talk about human activity as we organize to achieve certain goals. And again, we talk about the system modes here where you have real objects and conceptual objects. And as things get more abstract and more conceptual, then it increases complexity due to the simple fact that it's more difficult and takes more effort to communicate the context and the specific situation going on. And for the design mode, what we have is just a typical set of life cycle phases where essentially it's almost a mapping of a general problem-solving process where you kind of first look at and talk about what kind of problem you have, what you're trying to achieve. And then this first high-tech, typical high-tech commercial systems integrator, you got a study period where you do user requirements definition. And really, this is a study of what is the problem. And then you do a concept definition phase. Think, well, okay, maybe we can solve this problem in certain different ways. You come up with a selected approach, and then you implement that approach, and then of course then you operate it and then deactivate it. So in each case, it's essentially the same. You have an initialization process where you determine what type of system you're going to design, and then you go through and implement, develop, design, and develop and implement that system. And then, of course, you operate it. In the operations, you can see here that the deactivation and disposal is also part of operations. So those are essentially just the long-term general types of system life cycles when we're talking about having specific types of design activities. And it's good, to be able to identify what these are, but there's also different, once you get into a specific application and a specific approach, then there becomes, significant differences. For example, right now, there's a little bit of tension in the Agile world. Agile world started being coming out of software, and it's very dynamic and adaptive, where teams could be able to create and respond to new requirements and incrementally move forward and build very large systems a little bit at a time. Then, of course, that kind of conflicted with a very large top-down type of structured systems like were used to put together NASA, the man on the moon, other very large projects like we typically see in the aerospace industry, satellite systems, large aircraft, and so forth. But there's a conflict in both of these approaches. First, when you're doing a systems design and you just have you don't have a very structured top-down approach, which these system life cycles are like. Using an Agile approach, there's a real high density of information transfer among the individuals, the designers, and the people that are going to do the coding and the work. And that breaks down when the teams get, fairly, get to any size. They call it get past a 2-pizza team size, and Agile starts to break down. Of course, the 2-pizza team size, I'm going to say it's like 5 or 6 or 2 teams of 3 or something like that. But that's not really a very large team. And so they've tried a number of things with the Agile approach, where having layered, and where you have the conceptual people doing the conceptual Agile approach and the people doing the implementation. But that really breaks Agile, so that the size of your project and the context really impacts what type of effective organizations and technical development and system development organizations you need. And so there appears to be a need for something that can effectively translate the information, effectively transmit the information from the small Agile type teams to the top-down type of direction teams. And we believe that structural modeling may be able to play a role in this area. So that's one of the key things about the design. It's the size of the system, the way people are organized, and how can we apply these classical and currently modified techniques to alleviate some of the problems in the size of the system design teams. Then we go on and talk about what I call the Dahlberg approach to functional design. And Sten has worked at an aerospace company for many years and worked for other different companies for over a long period of time. I think he had a major part in approximately 50 major systems programs. And Sten's approach was basically the idea of a mission function. The difference between a mission function and a systems function. And most everyone in the large top-down system design groups, they don't make a clear distinction between the system function or the mission function. And and this confusion then creates a tremendous amount of extra work and just some very strong communication barriers. So conceptually, just by breaking the idea of function into the mission function, what is the primary goal, and then the system function, how are the techniques and processes and equipment that we're designing, how is that going to help us achieve the mission function? And you measure that achievement through operational effectiveness and measures of effectiveness. So you have well-defined measures that are used to decide whether or not whatever your architecture is going to meet the mission function. And then operational suitability, then once you have selected, you could have one or more architectures that can do the mission function, but they have different operational characteristics and operational profiles. And so then you need to come up with an operational suitability and take the operational suitability, and then you use that to prioritize and select the best system architecture. And the operational suitability, and of course, then the life cycle costs or properties of the system architecture that you assemble or propose to meet the mission function. And then, of course, risk is a property of the mission function, the system function, and the system architecture. And risk is always an important parameter that you keep track of and to manage and evaluate the ongoing system development effectiveness. So that's kind of, in a nutshell, the Dahlberg approach. And I think it's a really important way a high-level way of looking at these different activities and how they fit together and how they can be integrated to achieve success in very large-scale systems. And so one of the activities that happens, one of the ideas that when you're working to develop a mission function or any of your system components and what those functions are and the architectures, is you need to bring people together, bring large groups of people together to decide what has to happen. And then this is where the application structural types can play a role. And the application structural types that were developed by Warfield can definitely play a role here. Also, the work that was done by Hitchens in his Putting Systems to Work and a couple of his other books talked about how to evaluate these large-scale systems and their operational suitability. And at that, in what he made a transition from where he went from n-squared diagrams, which are used to conceptually put together an architecture and an interface flow, to automated n-squared diagrams that were used to, were computer-based, that were used to check and search a large configuration space of the system to find what Hitchens called the minimum entropy state, so that you'd have the highest value configuration of that system. And one of the things about designing using n-squared diagrams or these types of functional operational architecture evaluations is that these architectures and components, there's a large number of them. It takes a lot of time. It's very expensive to go through and do those by hand. And so one of the advantages of the automated n-squared chart is that you can actually give that task, that initial evaluation, that filter to a computer, and the computer can pick, the top 10 or the top 20 configurations, and then the team can look at those and figure out, select one of those or make some changes and put the computer back to work to look for different design configurations. So those are just some of the things that we'll be looking at as we go forward and pick a specific example and then talk about where you would actually do these types of activities and what would they look like. So, these fundamental tree structures, which you see in the Dahlberg approach, may be combined with other structural types like intent structures, priority structures, solution sequence structures, and so forth, to address a wide range of generic system design problems. And so that is kind of the goal here now, to start allocating these activities into certain types of areas within a large scale system design process. And then, of course, we have the structural modeling applications, where we had the basic structural models and interpretive structural models. These two were developed by Warfield. And then Mary and I added the structural integration modeling piece, where we bring those together. We pair the organizing relationships with specific sets of mathematical relations. And so this area, the structural integration modeling piece, is where we'll be now focusing more and comparing and contrasting what these specific different techniques and methods can do. So that's kind of the overview of what we're looking at. The abstract relation type and, of course, augmented model exchange isomorphism. We developed the augmented model exchange isomorphism to provide a logical, mathematical definition of the application structural types. The application structural types are just a pattern of structure that came out of specific areas in the came out of specific areas when they were doing these activities and these events for the interpretive structural modeling. So they noticed these patterns, they started looking at them, and so they gave them a name. And we further refined not only the name of this pattern, but we also then assigned a logical structure to them. And by assigning the logical structure, then that allows you to also bring in and look at other patterns that have the same logical structure, because that's really what you're concerned about when you're looking at the math, when you're mapping to the basic structural models, when you're mapping from the interpretive structural model space, the informal language to the mathematics. You really want to be able to have something that in the formal mathematics side that you can map the informal language to. So that's essentially what we're doing, starting the base for the AMEI and also the abstract relation type. And so here again is the, now we've picked the City of Seattle mission function just to, as an example, to start making this a little bit more concrete. All of these abstract things we've been talking about over the last couple of years. Now we'll start picking and tracking something, like this one that talks about the City of Seattle mission functions, provide a sustainable urban environment. Well, what does that mean? So they provide a lot of information on their websites and throughout the city to break that down and to document what that means. So then if that is their mission function, then how are they organized and what type of operational effectiveness do they have? So this particular part, we just picked the provide regional transport. So there's the light rail, and there's the tunnel, and there's a number of other things that were going on. So here we didn't look at a architecture for the total system mission function for the city of Seattle. We just picked provide regional transport. But you then would actually, if you wanted to do it for the host city, then you would develop a series of these types of system architectures and integrate them. And you would integrate them using operational suitability to determine which is the best. And then, of course, the life cycle cost. So we're looking for a specific, a real world type example. This is the one we've chosen. As I said before, if there's some other project that someone has a really strong interest in that would like to do an evaluation of that, then let us know, and we can always discuss a different example. But we need an example, I believe, to start making all of these abstract concepts much more concrete and communicatable to a larger group.
Joe, maybe you can repeat that last statement, because Peter just came on and he might be interested in addressing that.
Oh, okay. Well, so what I said was this City of Seattle mission function. In the City of Seattle, I picked this for, I think it was about 2008, 2010, about 10 years ago, started to reduce the all of these very abstract concepts to a specific application, to a real concrete example, so that it would start making it easier to explain and easier to communicate with people. So if there is any other example that people would be interested in that have a lot of energy behind, be sure to let us know, speak up, and we can always talk about that, using that example, and to go forward and demonstrate these particular techniques.
Does it have to be, do they have to be with technology, or could they be sort of social in nature? I mean, because some of the ocean related projects I'm involved in at the moment are more networking of people in different regions and in different disciplines, trying to design sort of or create a system architecture for communication and research.
Well, so let's think about that a minute. So if you have some type of organization that's got a mission function, right? You have some mission that
Right.
you're doing, right?
Mm-hmm.
So if you can identify a clear mission function and bound it within your group, and then you can decompose that mission function into its components, right?
Mm-hmm.
And then you're going to achieve that. You're going to do something. You're going to create something, some processes, some whatever, right? But you're going to create some type of system to support the achieving of your mission function, right? So
Right.
that would be over here, and you would have whatever those architectures are, and then you could do that. Then you would match that to your operational suitability and your life cycle cost. So in each case, now let's say, for example, looking here, the operational effectiveness and the operational suitability, this is where the priority structures and your intent structures from the application structural types make a play. Because you have to have values. You have to have metrics, and those metrics have to be grounded in what the group believes is important, right? And so on this chart right now, there's nothing that says type of priority application structural type. There's nothing here that says intent. application structural type or curriculum or how we achieve these things, right? But given a problem that's organized this way, then we can start mapping the application structural types to solving that problem. So if you have a problem that you would like to apply that to, if you want to, I don't know, can you open it up to the group? I mean, to work on?
Oh, yeah. Yeah, no, I could. I mean, since I read your paper earlier in the week, I've been thinking about this, and was going to listen in today to give me more information, and then seek a way to present it to you guys for some consideration. So that's a piece of work I've got going on in my head, at least at the moment. So yeah, in the future, definitely, very possible.
Okay, good. Well, our plan is, again, we'll go forward with this because this is kind of we already have some material with us, and we're going to continue to drill down into this area. So the sooner you do that, the better, so that we can, won't get very deeply into this and then have to transfer over to another one. But
yeah, because this is something that's gone. It's not currently in focus. I mean, this is something historical, really. You're sort of reporting on as an example. Is that my understanding? Sorry to be late, but
oh yeah, no. So okay. So the impetus of this specific City of Seattle example was, well, okay. Wait a minute. Let me back up a little bit further. So about 10 years ago, before I started working in detail on the logical components of the application structural types and looking at how that worked with Warfield's work, I was doing the dynamic type of system evaluation using evolutionary algorithms and genetic algorithms. And when I did that, I created 2 or 3 papers on those genetic algorithms and evolutionary computation approaches, and they were very abstract. And so the people that read those said, no way, we got to have an example. Give us an example so we can understand what this is. So I just picked the City of Seattle because it's large enough, right? And it's something everybody knows about, right? And I had the information available on the web. So I took that and then I mapped all of the specific things from the City of Seattle into this abstract type of genetic algorithm computation. So that's where the City of Seattle function came from. It is historical, and that was its purpose, right?
Okay.
But looking at this framework, it also presents a framework where you can map the application structural types. Where would I do an options tree? Where would I do a value tree? Where would I do an intent structure? Where would all these fit? Well, they would fit when you're evaluating operational effectiveness or suitability or life cycle cost, right? And so this is now need a grounding example, right, to start mapping these different types of activities together. And if we use this type of framework, then later on, if the design lends itself, you can use these other automated evolutionary computation approaches to actually search for the highest value configurations.
Thank you.
Yep. Okay.
So Peter, I guess as Joe said, the question is something that is well bounded and concretizable, so that it has to be socio-technical rather than just social, I guess.
Well, it is social technical. I mean, it's about the challenge. Okay, if you want to digress briefly, I mean, the one that I'm particularly looking on is how you coordinate the collection of data around the world on sea life in the sea, to build comprehensive models from the coastal zone to the benthic, to the deep ocean, And this is not done in a coordinated and consistent manner at the level of detail that's necessary to produce effective models of life in the sea and the various interactions. And so that's the proposal that we've written. And it just seems to me that, how you then organize a network of networks, people participating in that, and how you then go out and collect the data, which is the technical part of it, and how you make decisions perhaps on the different options, the different values, and the different intents, which I think I just picked up from what Joe was saying. And indeed, how you organize a network of networks of people doing this and encouraging them to be consistent and perhaps adopt, model standards for collection of data would contribute to the operational effectiveness and so on. So that's sort of my quick. Yeah.
Okay, that's interesting because it's sort of it's a middle out problem here. You're proposing a system that you think will achieve some kind of mission of sustainable ocean management, education, that kind of thing. So you're proposing a mid-level system element with the intuition that it would be of benefit and of greater benefit than the alternatives. So
the alternatives don't exist. That's the thing,
right?
I mean,
well,
it's all piecemeal around the world, basically. Yeah.
Business as usual is the one alternative, and maybe you could come up with another straw man alternative. If you could have three alternatives, one is pursuing your idea of the some kind of coordinated system. Business as usual is alternative 2, and something as a straw man for alternative 3, and then use this setup to test your hypothesis that your approach would be more effective at lower cost for achieving the mission than the alternatives. Does that make sense, Joe? Does that, because he's not working from the mission backwards.
Yeah, that's the point.
Sustainable oceans.
But there's okay. So this is a typical example of starting in the pre-conceptual phase, and so this is standard type of conversation and ideas. So what you have is essentially what I used to call 3 up and 3 down, and so Peter's talking about some system, okay, and so whatever the mission function of that system is, which is collecting data to achieve some function that's going to feed into a higher level of abstraction function of system, some kind. That's got to feed into something. So you've got to have at least some kind of idea of what that is, right? And so why do we need this data? What would we do with this data? Say we achieve our mission function, so what, right? So what does this feed into, and does it just at that level? And if you can think of something that's higher than that, that's fine. And then at your design level, whatever it is with this ocean literacy or ocean data or collecting data in a certain way, right? Then you say, okay, now I've got to collect the data. How am I going to do that? But so what?
Yeah, the data is being collected already, but it's inconsistent, and it's perhaps incompatible, and it's incomplete. So it's more about building a social network of people who are all committed to understanding life in the sea, but do not together such that the data is comprehensive or compatible. So the development of models about understanding life in the sea is not as accurate or complete as it could or should be. I think that's my best way.
Okay, so that in that particular case, then what I hear you saying is that there are a there's a number of decentralized activities going on, all kind of driven by their own methods and motivations about understanding the sea.
Yeah.
But they're not integratable. And they're not integratable because there's no higher level integrating language, methods, functions, values, intent, so forth, right? To do that.
Some of it, but not complete.
But not complete. Okay. So that's poorly, some of the stuff there is kind of really a poorly defined system. So those are the things that you could definitely use these types of techniques effectively on.
Mhm.
Because again, you said, well, it's a social technical system, but in the design front end of this, right?
Mm-hmm.
Then the interpretive structural modeling application structural types, those then become very effective here. That's what they were designed for, the social bit,
Right.
to bring it together. So
Yeah, I get that. Yeah.
and so now if actually that once you do these activities, then if you start having some type of recognized mission function that's going to be achieved by some social technical problem that has a social technical system that has a technical component to it, then you can start applying these other types of techniques more effectively.
Right. Okay. That's helpful. Yeah.
I think, this is very interesting because we're facing the same thing in the System Science Working Group and at ISSS, that there's an assumption that sort of this middle out problem where you start with an assumption that the design you have in mind is going to achieve some beneficial ends. You're not working backwards from the mission and with an open mind to what would actually achieve the mission. You're saying, if we developed a definition of system science, that would be really helpful for systems engineering. But you've made a premature commitment to the design of the system, and then, am I making that clear? It seems like it happens all the time that people don't work backwards.
It
from the
does.
mission.
Yes.
Yeah.
It really. So that again is the key reason for the 3 up and 3 down.
Right.
So that if most people do that, most experts, people that have spent their lives developing skills, knowledge, and abilities in a certain area, they come to to a problem with that type of bias, right?
Yeah, and non-experts too. The various degrees of everybody seems to work with some kind of design bias and a vague sense of what the mission is.
Right.
And I know Jack, as well as you, keeps trying to get people to focus on the mission. Maybe taking one of these middle out cases and applying your methods to a middle out mentality would be a really good way of showing, the value of the.
I think we should pick
techniques.
one or two. I mean, I think you mentioned in COSI. I mean, ISSS is in the same situation, and I've got ocean examples, obviously. I mean, a couple of them. So I don't know how many we need, but I think actually working through this, Joe and Janet and Mary with some, and Kevin with actually a couple of examples we're wrestling with would be extraordinarily helpful.
Okay. Well, that's great. So I think that I'll plant this idea in your head again about the 3 up and 3 down.
Mhm.
So you're talking about middle out, right? So the idea is that whatever you think is the top, right? What is above that? So now you have to think about why are we doing this? Why is it important to the larger world, right? That might not, right now, you might not have a very good example of that. And you may not be able to make connections with it, but as you go forward, right? But it's been my experience that people that look at this, they're able to, over a period of time, especially during the conceptual design phase, they're able to come up with different views of that top level where it fits in, and they get and in thinking about it, then it helps refine the mission function of itself, because it's got to fit into something else, right? It's got to have other interfaces. It's not blue sky.
Right.
And so that kind of helps. So the idea is, okay, whatever your mission function is, if you can just write down your mission statement, Peter, and whatever it is.
Well,
then,
I think that coming up with something that's abstract, something like provide sustainable urban environment, is not hard to do. The problem is actually working backwards from that with some kind of commitment to getting it out of the wishful thinking. Everybody can agree on that kind of blue sky kind of language. So sorry, Joe, I'm sorry to interrupt your presentation, but I think this is really interesting. It just occurs to me that Gary Smith, who's now the VP for Systems Practice at ISSS, and he's the editor of the System Engineering Foundation section of the CBUC. He and a few other people, including I'm on that group as well. I don't know if Peter, you are. We're going to be working on a systems engineering management plan to develop a foundational theory for systems engineering. So he works at Airbus. He's pretty high up at Airbus Systems Engineering, and he wants to tackle this question of providing system science foundations for systems engineering using some of these systematic tools. So that actually might be a very good problem.
Yeah, it would be an ideal kind of recursive application of this to that particular problem as it relates to Nkosi and what Gary and the team, are trying to do.
Right.
Okay.
That would provide you with some kind of support, for development of this core problem. But get back to what you're doing. Okay.
Okay. So on that, I'm just gonna I'll just bring in a little more background on the Dahlberg approach, right? And so what Dahlberg and his associates call this is they call it the scientific systems engineering approach. That's their name for it. And it comes right almost, word for word or concept for concept out of the original Air Force systems engineering manuals way back in the 60s. And so these types of concepts have been around for a very long period of time. They've been replaced by less obvious, I guess, let's say, approaches. So there's a deep history in this type of model approach. And it's basically designed as being a scientific, operational effectiveness, get your hypothesis, do your tests, and that's what the measures of effectiveness and all that are about. So I think we're all on the same page there. If anybody wants to come up with some general areas and start, a round of emails so that we can start to formalize this, that would be great. All right, so that was the City of Seattle example. Okay. Now let's go back here a little bit more, and just the idea is that here we have a higher, we have a fairly high level of a mission, provide sustainable urban environment. Okay. And then that's broken down, provide social equity, practice environmental stewardship, support economic opportunity. And so how do you do these things? So they say, okay, let's just look at one component, provide regional transport. And really in Seattle, that's important because of the constrained land area. There's all the water around Seattle, and it's really constrained between Lake Washington and the Puget Sound. And there's a tremendous amount of automobile traffic that's just choking the area. So regional transport is, because of the system, because of the way things are organized, is really important. So there's a lot of that going on right now. And there's a lot of involvement within the counties and the cities to reduce the amount of car traffic, increase buses, increase light rail, increase trains. And so that's over here. We look at the operational suitability of the light rail transport. So regional transport is going to be a combination of light rail, buses, the basic, not only the light rail, but also the regional rail. And so all these things then would have to be aggregated to see whether or not you're achieving, your goals on your sustainable urban environment by some metrics. You'd have to come up with your metrics. And that's where the application structural types all help to create those. Okay. All right. So now the abstract relation type dynamic analysis. So as I said, about 10 years ago, we stopped doing the evolutionary programming and evolutionary type of genetic algorithms and started looking at going through and looking at Warfield's logical work in detail. And that took a little bit longer than I thought, but I think we now have an approach that we can apply across a very wide range, if not the complete range of types of logical situations when we're dealing with groups and developing language. The one thing here in the automated n-squared chart with Hitchens, 2003, Hitchens was addressing this pipeline of how you develop a conceptual system to meet a dynamic changing problem. And when he introduced the idea of the n-squared charts for evaluation and the automated n-squared charts using the entropy evaluation. But he then pointed out that you only have one, this is only one configuration that you started with, and there's probably others. There's other configurations and other values and other types of insights that are important to get into the mix. And he proposed using Warfield's ISM, but unfortunately, he equated ISM mechanisms with the pairwise type of evaluation that's done with Satté's work. And of course, Satté's work is not anywhere near, or even, they both use matrices, but that's it. One is Boolean logic, the other is, types of floating point rational numbers. Satté's method allows intransitive relationships where Warfield's does not. So looking at that work is what really, in my mind, triggered the idea for the AMEI and the ART, because even though Hitchens associated ISM with Satté's work incorrectly, the methods and techniques that Hitchens was talking about appeared to add value, and it seemed to be an area within systems engineering that we really hadn't been addressed yet. So what I felt was needed, what Mary and I felt was needed, was a very clear way to talk about the differences in all these techniques and talk about them in such a way that they could be identified and they could be separated with each other, and their value and their type of application space very well delineated. So that was the impetus for the abstract relation type at AMEI, so we can basically have many more types of natural language mechanisms and names associated with these particular application structural types, because the mathematics depends on the logic, not on the natural language name. You can have many natural language names that basically fit to the same logic, so that the math will be the same. And so the idea is mapping and picking the right natural language name for your context of interest, for the group of people you're working with. And that's an area where, some work probably should be done to figure out how you test that out. I've come up with a few set of simple rules I think that can effectively calibrate people, but if we go forward and get a group of people working together, then we can test out those calibration techniques. So anyway, we went through and worked on the n-squared charts. This was, what happens here is that on the dynamic art approach in the n-squared example, we do this differently than Hitchens or the other genetic algorithms or evolutionary programs do, because we don't work on one cell at a time. So most all evolutionary programs mutate a cell at a time or a connection at a time. And we basically just deal with basically a system or a subsystem at a time. So the system is a relationship mapped over a set of objects. So here we move two objects that are related. So you have to move the objects as a pair. You can't just move one object. You can't mutate just one thing. You have to mutate a pair of things. And so that was, we implemented that and were able to test it and reproduce quite a bit of published literature within the systems engineering community at that time, and some within the DSM community. We've got papers on specifically how this works, but the idea is that if you use your structural modeling techniques to come up with an initial configuration, you don't know if that initial configuration is the highest value. So it could be like this one here with no obvious pattern, it's unordered. So you come up with a value system, and then you run the evolutionary algorithms and you get a pattern, and from that pattern you get a different order. And then that order can be evaluated by the human subject matter experts to determine whether or not it is more valuable or more appropriate. And these mechanisms, then this approach allows the computers to generate, let's say, 5 or 10 alternatives, very high value alternatives to let the subject matter experts talk about. Otherwise, there might be hundreds or thousands or tens of thousands of alternatives, and people just say, oh, I got this one, let's go with it, right? They don't really search for higher value ones. And then here, the systemic clustering around diagonal. So basically, we did these three-dimensional number spaces here. And then we did these three-dimensional charts. And I call it, instead of a fuzzy number, I call this a system number. So this basically, within the value space, you would have this one here would drive either all of the systems. If you're minimizing around the diagonal, if you're maximizing, it would drive them to the corners. This one here, there's a step offset, so this would drive everything to lower triangular. This would be used a lot in sequencing of programs, types of program network design, drive everything to lower triangular. That's what they want to do. And then the other options. So anyway, these types of system numbers then would again generate more patterns that you can identify with specific types of system properties that are valuable. So we've got about 6 minutes left here. So So what we're going to do is basically go ahead and look at, we discussed all of these application structural types. Now we'll be going back and picking something. It seems like the group has got some ideas that we can work on and start aligning those so people get a better idea of where and how you would use those. Had a very nice conversation with Ken Lloyd over the last couple of weeks, a little exchange, and he introduced me to NEAT and HyperNeat, which is a evolutionary type of programming approach. I was able to quickly find some books and look at it, and it appears that these types of evolutionary programming approaches would also be another valuable addition to the evolutionary programming components that we're using when we're searching for very high value configurations. So going forward, we're going to just pick a specific example, show where and why these techniques are valuable, how they work. I have gone back and I've started working on the binary matrix examples. One of the things that I found when I was doing the original work to validate things that have been published was very tedious. There was lots of mistakes in the transfer of the information. So what I did was I developed a set of standard matrices that people can use if they want to test and compare their different methods. And I've upgraded and updated that, and also updated the current proof of concept software on GitHub. And I've put out the new, a couple new programs this week, actually some new methods. And I'll continue to do that as we go forward and develop it more. So, we're looking now at system science research, and basically we're looking at maybe following research questions, right? So we're science, we do research. Research is based on research questions. Then you develop tests and hypotheses. So these are some of the research questions we have. And now we will develop techniques and go forward and maybe generate some hypotheses and do some tests. So we have about 3 minutes left. Is there any questions?
Well, I put it in the chat. I mean, how can we as a group here start working on that? Would it be to identify a couple of, what is the first starting point? I mean, I put up 3 examples. Janet mentioned the NCOSY chapter 2 on the CBOC. I and many of us, and Janet and you probably, were all concerned about the future of the International Society for System Sciences. And I'm working on this ocean and life in the sea network of networks to gather data. What's the first step that we need to do as a group? Well,
so the first thing that has to happen is you have to identify the mission function. Remember, Kennedy said this is what we're going to do. We're going to put a man on the moon by the end of the decade. Boom, mission function. So for each one of those areas that you're thinking about, you got to have a mission function. It's got to be bounded. This is what we're going to do. This is when it's going to be done.
Right.
Right. That's interesting case though, because that's not a mission. That's a design. It's not a need. Well, maybe it could be seen as a need, but it it wasn't expressed in terms of values. It was expressed in terms of
but it was a clear element. It was a clear direction. Put a man on the moon.
Clear. Right.
Yeah. That's how things have changed since the 60s, right?
Right.
So you got all these other, just what's the mission? Boom. Clearly state the mission. What is it? When does it have to be done?
Now, let me say that, Joe, so did you have a call last week as well?
No.
Okay.
No, we were out of the country last week.
Okay. So next Saturday is the first call meeting of the what he's calling the systems planning, strategic planning for system science. It's trying to develop concretize in a systematic way a plan for developing, clarifying system science for systems engineering. And obviously, this work should be a big part of it. Warfield's work, your work, needs to be represented in how system science is understood, in what it can provide for systems engineering. And then, as we're discussing, maybe this could also be used in the process of the strategic planning to clarify system science. So that call is, because someone is participating from India, that's at 7 a.m. Pacific time next Saturday. If any of you are interested in participating, and I see, Peter, you're on that too. I think that as opposed to the ISSS question, which is, sort of folded in, how can the value of ISSS be clarified and concretized? So I'd say that the Gary's project, and maybe something that you could define for oceans, are the most interesting. I think it would be great if we could bring this into the NCOSE, Gary's NCOSE effort, because
absolutely.
I think that would really bootstrap both efforts. It would elevate the profile of this work, and clarify for the rest of NCOSE what is going on in the System Science Working Group. It's a bit of an effort to bring everybody together, and I don't know if we can get Gary to watch this video. You can certainly read the paper, but I'm going to advocate very strongly that that this should all be folded into into Gary's work, which will be a bit abstract still if it doesn't take this kind of approach. So that's my contribution.
Kevin, do you have any comments? Okay. Well, I would just, if you're interested in this, the first step is the mission function. Figure out what you have to do. You get those, then we can work on the next thing, which is to be able to decide whether or not the mission functions need to be decomposed, or we need to start looking at a high-level mission architecture. Now, as I said, this was put together by a guy who's worked on about 50 high-level programs, right? Very complex programs. And I think probably all 50 of those specific programs had initially the same mission architecture, which is perform the function, prepare to do the function, recover from the function, integrate information, be prepared to do the next function. So there's kind of a template for this. So basically, a clear mission statement, a clear mission function is the first thing. Come up with those, then we can start decomposing it and looking at how these other things would fit in any situation. Right.
I'm sure that Gary's been planning to use the systems engineering management strategic planning that Airbus uses, and Airbus is probably their system is probably very compatible with this approach, or probably already folds it in, or but what you bring to it is tying in the Warfield, the different application types, that kind of thing. So I haven't looked at the Airbus material. There probably is no incompatibility there. Probably will be strong compatibility. Anyway, so interesting.
Okay. Well, with that, I think we better go ahead and
thank you.
and the next meeting will be in March, the 7th. And does anyone want to do a meeting on the 22nd? Okay.
Yeah, I'll say, especially if we can get Gary to join, we will,
Okay.
why don't we try to see how this is looking for using that as a test case.
Okay, then Jen, I'll let you lead the 22nd, and then Mary and I will have our paper and so forth ready again for the 7th. And
Very
we'll
good.
see everybody in a couple of weeks.
Okay, great. Thank you.
Thanks.
Bye-bye.